In this video, I'm going to be showing you how to use PCA within PLS Toolbox. Now, before watching this video, I would highly recommend watching some tutorials on PCA on YouTube, just in case you're not familiar with the concept and some of the theory behind it. And there's also a link in the description to a video from Eigenvector themselves showing you how to use PCA in PLS Toolbox for a more general application. And that'll be useful for sort of giving you a feel for the software as well as giving you some intuition on how PCA works. Now, the first thing you're going to want to do is just make sure you're connected to Carlton's VPN, or else PLS Toolbox is not going to work. And now in this example, I'm going to be looking at this data set right here. So we're in our workstation.m script that I showed in the previous video. And so I'm going to be looking at this Lysate NOV 2017 T data set that I have. So first I'm just going to run what we have here, import the data, and we'll just take a look at what that looks like. So this is what our data looks like. In this particular data set, in the first three columns, we have donor number, we have dose applied to the blood, and in the third column, we have serial number. Everything else to the right are all Raman intensities. Now, when it comes to PCA, the way you want to be thinking of all these spectra, so just remember that a spectrum is a single row. The way you want to be thinking of these is that each number here is a coordinate. So if you look above, each column actually represents a variable or a Raman shift. Imagine you're plotting this data and we have, say, 1,200 or so different variables here. Well, in order to plot all 1,200 variables, you need 1,200 axes or 1,200 dimensions. So in order to plot this spectrum here, for example, you would go this far, so 4.43 times 10 to the 3 on the first dimension or on the first axis. And on the second axis, you would go this far into the axis. Third axis would have this value, fourth axis would have this value, and so on. And eventually, you have the coordinate of a point in that particular space with all those different axes. Now, obviously, 1,200 different variables or 1,200 different axes or dimensions is really hard to visualize and it's hard for us to interpret. So PCA tries to reduce the number of dimensions down to just 2 or 3 or maybe a few more. But the point is that we're reducing the dimensionality of the data significantly. So instead of plotting this spectrum right here using 1,200 different axes, you might be able to get away with just 3 axes or just 2. And that way you're able to interpret your results a lot better. I'm going to go back now. And what I want to do is actually extract the donor 17 data, 0 and 5 gray. So to do that, I'm going to create this variable all where I will store the pre-processed data. So I'm going to call the prepset function as I showed in the previous video. I'm going to input the data itself, the raw data. I'm going to choose donor 17. And I'm going to ask for the 0 and 5 gray data. And I want all the serial numbers. For pre-processing, I'm just going to copy and paste what I have right here. So these numbers are kind of my typical pre-processing order. I'm going to hit it with a semicolon, hit run, and it's done. So taking a look at all, you see that we have our pre-processed spectra now. We have these 0 gray measurements and these 5 gray measurements. Now the number of spectra that we have has actually been reduced significantly, and it's probably because of the really high number of spectra I'm averaging here. So I'm averaging 22 different spectra for each spectrum in the pre-processed set. So what I'm going to do actually is just quickly lower the average number and run it again. And when we look at our all variable, we see we have a lot more data to work with. All right, so there are two ways to access PCA in the PLS toolbox. The first way is to open up the Browse window. So to do that, just type in Browse, and this window is going to pop up, the PLS Workspace browser. Once it's fully opened up, you'll see you have access to all the different tools that come with PLS Toolbox. So in our case, PCA is actually found under the decomposition area here. So if we look down here, we'll see Principal Component Analysis, and in order to open it up, you just have to double click on it. The starting analysis window is going to pop up. It'll take a second, but PCA then opens up. Now I'm quickly just going to close this because I wanted to show another way. It's a bit of a faster way to open up PCA. And to do that, all you have to do is type in PCA. It's going to bring up this starting analysis window again, and it'll skip the browse menu and go straight to PCA. All right, so now we're ready to apply PCA to our data. The first thing you want to do is actually input the data. So to do that, we're going to go to the X block right here. I'm going to right click and click on Load Data. This Select X block data window pops up, and it shows us all of our workspace variables in MATLAB. So the data that I want to import is actually in this All variable. So I'm just going to double click on that. And once the X block goes dark blue, it means that the data has been imported into it. We can view our data by right-clicking on X block and hitting Edit Data. And this dataset editor pops up. So you can view all the different columns and rows you have in your data. And now, since we want to actually apply PCA to the intensities and not these first three columns, we need to exclude them. So this first column containing the donor number and this third column containing serial number, they're just kind of useless for the PCA. They don't really matter. So we can exclude them by selecting the two, right-clicking, and then hitting Exclude Selected. And then once they're grayed out, they're excluded from the data. They're not going to be used in the PCA analysis. And then for this second column, I actually want to use it as a class, because once you use this column as a class, it's going to give a certain shape and color to all the points in the principal component analysis plots. So if you just right-click on that column and go down to Use as Class, and then hit OK, you'll see that now all of these spectra are belong to class 1. And when you look at the plots, you're going to see that they appear red. So it's just a way of distinguishing your 0 grade data from your 5 grade data, or just any data of different classes. The data down here, all these spectra, they belong to class 6, which is our 5 grade data. So once we're done with that, we can exit out of the dataset editor. And the last thing we want to do before running the model is to click on this P right here. And over here, we can actually do some pre-processing. So if we click on Edit Pre-Processing, another window pops up, and you'll find that there are a ton of different pre-processing methods that PLS Toolbox offers. Now, I'm not going to check any of these because we already applied our own pre-processing within MATLAB. So I'm going to close this, but there is one pre-processing that I do want to apply. And if you just hit the P and go down under Basic Methods, I'm just going to change this to Mean Center. So essentially that just means it's going to mean center all of our spectra. And if you've watched some basic principal component analysis videos on YouTube, you'll understand what's the point of mean centering your data and why it's necessary. So finally, once we have the X data imported and we have mean centering selected, what we can do is just click on this green model button, and it will create the PCA model. I'm not exactly sure what the criteria is for how PLS Toolbox decides to keep a certain number of principal components, But if you want to keep more or less, all you have to do is just select a row. So let's say I wanted to keep 10 principal components instead. Select a row and then just re-click the green model button. And then it will recalculate the model for you. Now that we have our model created, we can start looking at scores and loadings. So in order to look at the scores, you just want to click on this little Erlenmeyer flask icon at the top, and it will bring up this new figure. So in this figure, if we expand it a bit, we'll see 3 different subplots. The first one on top is a hoteling t-square and q-residual plot. So this is kind of useful for detecting outliers. If you find any spectra that go beyond these blue lines over here, which are the 95% confidence limits, then you might want to consider those spectra as outliers. And remember that each point you see here, so all these red diamonds and all these yellow circles, they all represent a single spectrum. Next, in the middle plot, we have the actual scores. So on the x-axis, we have scores on PC1, and on the y-axis, we have scores on PC2. And we can see how the data separates out in that principal component space. And then in the last subplot here, we have scores on PC1 on the y-axis and sample on the x-axis. So instead of showing you scores in 2 dimensions like we see in the middle plot, it's just showing you scores along 1 dimension. In order to bring out one of these plots into its own figure, you just want to double click on one of them. So to me, I think the most interesting plot is the middle one here. So what I'm going to do is I'm going to double click on it. And it will create this new figure. You will also see these plot controls off to the side. Now there are lots of ways you can control what you're displaying in your figure here. So the first thing I like to do is actually get rid of this 95% confidence limit. So to do that, just go to the very bottom and uncheck this box right here. And that gets rid of that dashed blue circle. If you want to look at different principal components, so for example, we have principal component 1 on the x-axis right now, but what if on the y-axis we want to look at principal component 3 and not principal component 2? So to do that, we just go to the section in the plot controls here that has a bold Y next to it. And instead of highlighting PC2, we want to highlight PC3. And now, as you see, the y-axis has updated and it's showing us the scores on PC3. We can select any PC you want really. So now it's looking at PC6 and PC10 now. But since PC1 and 2 are usually the most interesting, that's what I'll keep it at. If you want to look at principal components along a single axis or a single dimension, on the x-axis, just change the data to sample. And then on the y-axis, you can put principal component 1 or any other principal component you'd like to look at. I'm going to change it back to PC1 versus PC2. So one thing we can do, so we don't forget what our data actually represents, is bring up a legend. So under Insert, hit Legend, and then you get this legend here. So in our case, the red diamonds are class 1 and the yellow circles are class 6. If you recall, class 1 and class 6 correspond to 0 gray and 5 gray in my case here. So what I'm going to do is just double click on their names to change them to 0 gray and 5 gray. You can also do all the other usual things, for example, adding a title. And whatever else you'd like. If you want to fancy up your plots, you can actually add confidence ellipses around your data points. So if you go to this button right here, if you click on it, you have a bunch of different options. The one I like using is the confidence ellipse. So when you click on that, we'll see we get these ellipses around our data now. So it helps to clearly show the separation in the data, which is something nice. You don't have to use confidence ellipses though. You can choose points in sequence. You can also choose border points. There's the spider, as well as mean at each x. I prefer using the confidence ellipses, so I will stick to that. Let's say you want to know the row number of each spectrum that's plotted in this graph here. All you have to do is just click on this button right here with the blue dot and the 1, 2, 3. Hit OK. And then it just shows you the number of each row for each spectrum here. So if we go back to our data, so go to the X block here, hit Edit, so we can actually view our data. We'll see, for example, that this yellow point right here with the 26 right next to it corresponds to this spectrum. So spectrum in the 26th row of our data. If we look at this red diamond right here, which has a number 3 next to it, that corresponds to this spectrum, corresponding to the 3rd row in our data. I'm going to undo that just to make the plot a bit cleaner. Now, something interesting I'm noticing is that we have a lot of separation along the first principal component. So if we were to look at just principal component 1, so let's change the x-axis to the sample and scores on PC1 on the y-axis. I'm also going to remove the confidence ellipses here because they don't make as much sense. So you'll see that along principal component 1, there's a very nice separation. If we were to look at principal component 2 only, there's really no separation along principal component 2. So obviously principal component 1 seems to be our discriminating principal component. So what we want to do actually is look at the loadings plot for principal component 1 to see which wave numbers are contributing to this separation. So I'm going to close out of these figures. And to look at the loadings, all you have to do is click on this green curve right next to the Erlenmeyer flask, and it will bring up a loadings plot. So this is now our loadings vector. As you can see, we're looking at PC1 at the moment, and the percent sign that you see next to PC1 is actually telling you how much variance within the data this principal component has captured. So in this case, PC1 is actually capturing 82.59% of the variance within the data. If we go down to the other principal components, so PC2 for example, we'll see that the amount of variance captured by PC2 is a lot less, just 4%, and the resulting loadings vector is a lot noisier and looks a lot more random. Same with PC3 and PC4 and PC5 and so on. Now, the way you can interpret this loadings plot is to think of it as a spectrum that tells you the weights of each Raman shift when it comes to calculating the scores along the respective principal component. In other words, this spectrum right here is telling us which wavelengths, or which wave numbers are responsible for the separation between the 0 gray and 5 gray data. So as you can see, this peak right here seems to be strongly related to separation of 0 gray and 5 gray data, as well as this peak here, this peak over here, this other peak over here, and perhaps this peak as well. Any peaks that share the same sign are going to be positively correlated. So for example, these 3 negative peaks down here are all positively correlated. So essentially what's happening is that whenever we're increasing the dose or going from 0 gray to 5 gray, what's happening is that any peaks located at these Raman shifts are increasing together or decreasing, just whichever way, it doesn't matter. The point is they're positively correlated. Another effect that's happening is that any peaks that are opposite sign are going to be anti-correlated. So when we go from 0 gray to 5 gray, what's happening is that the peak that's located at this Raman shift is actually going in the opposite direction of the peak that's located at this Raman shift. So what might be happening is that the peak at this Raman shift is increasing, when we go from 0 gray to 5 gray, but the peak at this Raman shift is actually decreasing. And same with like these two, for example. When we go from 0 gray to 5 gray, this peak might be increasing while this peak would be decreasing. Or it could be the other way around. This peak might be increasing and this peak might be decreasing. One thing to know is that we haven't given PLS Toolbox any Raman shift information, which to be honest, I'm not even sure if you can. So what you're looking at on the x-axis here isn't Raman shift. It's actually just the order of the variables that appeared in our data set. So this 600 here is not 600 wave numbers. It's just the 600th variable or the 600th column in our data set. Let's say you wanted to plot more than one loadings vector at a time. All you have to do is hold Control and select any other individual loadings you want to plot. So let's say I want to plot 1, 3, and 4. I just select those three. Or another way is to hold Shift and select a range. So I'm holding Shift right now, and when I click PC5, it's going to select all principal components up to and including PC5. So that's really messy, so I'm just going to stick to plotting PC1 and PC2. The last thing I want to do is just insert a legend here, so we remember which loadings vector corresponds to which principal component. So the blue line corresponds to PC1, and the orange line corresponds to PC2. So that is pretty much it for principal component analysis in PLS Toolbox. There's a lot more you can do, but in terms of just basics and what you'll mostly be using it for, I think what I covered is pretty much it. So I hope that was helpful, and in the next video we'll be looking at how to use PLSDA in PLS Toolbox, which is works quite similar to how PCA does.